Good afternoon, everyone. My name is Maryam Bonyadi, and I'm a senior specialist working for Lloyds Register. I'm here today with British Gear Association for a Technical Awareness Day. I'm a chartered engineer and a professional member of Institution of Materials, Minerals and Mining. I am also a committee member of BSI and Institution of Corrosion. I worked as a lecturer in mechanical and materials engineering and as a process engineer in the oil and gas industry. I have worked as a materials engineer involved in a wide range of industries such as oil and gas, petrochemical, automotive, power and mining, and of course, maritime industry. This enabled me to attain an in-depth knowledge and experience in a wide range of materials and components. I have technical and specialist knowledge of mechanical failures and corrosion mechanisms. My primary responsibility is to conduct failure investigations, to identify failure mechanisms, quality problems, product misuse, design issues, and of course many more. Today, I will be introducing Lloyds Register and services a law provides. I will also introduce Technical and Failure Investigation Department, our team, our experts, our facilities, and some of our capabilities. Later on, my colleague and Instrumentation Lab Manager, Richard Merchant, will be providing some introductory information about strain gauges and strain gauge measurements. Following this, my colleague and metallurgical lab manager, Dr. Chen Zhu, and I will go through some failure investigation case studies. Lloyds Register is a global professional services company specializing in engineering and technology for the maritime industry. We are the world's first marine classification society, created more than 260 years ago to improve the safety of ships. LR is an independent organization that is owned by the Lloyds Register Foundation, which is a charity dedicated to research and education in engineering and technology. Us in LR, we are known for our integrity, impartiality, and technical excellence. Our compliance business is a leading provider of classification and compliance services to the marine and offshore industries. This is to help our clients to design, construct, and operate their assets to the highest level of safety and environmental compliance. In the race to zero emissions, our solutions and technical expertise have been supporting a safe and sustainable maritime energy transition. Our advisory services have been offering our clients support and solution on business operations, energy transition, risk management, emergency response, failure investigations, condition assessments, and many more. Such services are provided by different departments. Our Technical and Failure Investigations Department sits within the wider Professional Services Department, which provides engineering consultancy services, failure investigations, condition assessments, as well as engineering analytical investigations. The manager of the Technical and Failure Investigation Department is Alan Sharp, who has been with LR for over 26 years, giving him an extensive level of knowledge and experience as a marine engineer and principal surveyor in countries such as China, Korea, Vietnam, and of course the UK. Some examples of failure investigation services that we provide are associated with machinery failure, such as failure of shafts, bearings, gears, cylinders, rudders, propellers, and many more. In some instances, we need to carry out metallurgical and/or analytical investigations to determine the root cause of failure. We also carry out shaft alignment analysis, noise and vibration modeling, testing, prediction, assessment, as well as fatigue analysis. We have our metallurgical and instrumentation laboratory, a stone throw away from the GTC office in Southampton, which is very convenient. Here you can see our instrumentation lab. Hopefully in the future, a technical awareness day with British Gear Association and LR will be held in person, and we will then include a tour around our lab. But for now, I can just give you a quick overview of our facility and equipment. Here you can see our machining area with milling and CNC turning machine, surface grinder, bandsaw. These machines enable us to section large samples and prepare samples for mechanical testing. We also have tensile and Sharpie testing machines, as well as hardness testing and Bruno Vickers and Bruno hardness tester. We also have a dedicated metallurgical preparation room and a fume cupboard, and are very high tech and well equipped as SEM EDX. In the next few slides, my colleague Richard Martin, our instrumentation lab, will be going through some of our capabilities in the lab and explain how strain gauges and strain gauge measurements work.
Hi, I'm Richard Marchant, and I work at the Technical and Failure Investigation Laboratory, usually referred to as the TFI Lab. One role of this section of the department is to undertake field measurements, and the laboratory is here to support this function, both in terms of equipment and personnel. This includes calibration of equipment, either internally or externally, in addition to maintenance and development. Most of the measurements we undertake are short-term, often only a few days in duration, but can extend to a week or two and occasionally longer. I will quickly run through the main types of measurements we can undertake. There is insufficient time here to provide details of these, as they are each a subject in their own right. However, hopefully this will provide an insight into the scope of measurements undertaken by TFI. We can undertake most of the measurements simultaneously, which provides greater scope for identifying the cause of any failure and assisting in an investigation. Vibration is one of our most common measurement parameters. We use both accelerometers and velocity sensors for vibration measurements, and have charge, MEMS, and IEPE type sensors. Shown in the picture is a typical general purpose accelerometer. TFI can also undertake modal measurements with instrumented hammers to excite structure to establish mode shapes and natural frequencies. Displacement measurements are usually undertaken to establish displacement variation relative to other structure or equipment. We usually use eddy current or laser sensors for measurements of rotating shafts to establish, amongst other things, radial vibration and to obtain orbits. For measurements involving non-rotating targets, contacting type sensors such as LVDTs can also be used. We also undertake noise measurements. These are usually recorded using handheld sound level meters, as seen in the picture on the bottom left. A common use within TFI is to undertake measurements to confirm passenger and crew spaces meet noise and vibration regulations. For strain, I have been asked to provide a little more detail, so I will come back to that shortly. Pressure. We use pressure transducers for measuring pressure in fuel lines, coolant lines, engine cylinder pressures, and hull surface pressures as a result of propeller interaction. The picture shows a pressure transducer and mounted in a fitting that screws through the hull to measure pressure pulses from a ship's propeller. Main propulsion shaft bearing and bore alignment measurements, for which we use optical and laser alignment methods. Shown bottom right are optical targets mounted in a bearing. Shaft alignment of installed shafts, for which we use both strain gauge and jacking methods. Ideally, both methods are used as they are complementary to each other. Some additional measurements include the following. Load and force using load cells and load links, for which we have a range of capacities from 5 tonnes to 100 tonnes. The picture shows some of our available load cells. Temperature measurements, usually undertaken with thermocouples to measure temperature as required. Propeller observations can be undertaken using low light cameras coupled to borescopes. These borescopes are fitted into viewing bolts and mounted in hull penetrations to provide real-time video for investigation of cavitation issues on propellers. The video in the bottom left is an example of this capability and shows a badly cavitating propeller on a large container ship. We can also measure vessels' roll, pitch, yaw and slip angle using a combination of inclinometers, accelerometers and GPS. GPS is also used during sea trials for establishing speed, position and rate of turn. Shown is one of our differential GPS units. Finally, we have a range of general metrology equipment ranging from hardness probes, surface roughness gauges, thickness measurements using ultrasonics, and basic geometry measuring using micrometers, verniers, etc. I have been asked to talk a little bit about strain gauges. These are our primary method of measuring strain. They come in many forms, but in TFI we mainly use foil gauges. Foil gauges are a device with a single continuous conductor arranged in a grid, as shown in the left-hand picture. In the graphical image shown in the centre, it is easier to see the single conductor arrangement and its orientation to the strain direction. These devices are bonded to a surface, usually with an adhesive, and give a change of electrical resistance proportional to the change of the surface strain. If compressed, the resistance reduces, and if pulled in tension, the resistance increases. When strain gauges are connected in a Wheatstone bridge configuration, as in the right-hand image, they can be connected to strain gauge amplifiers or conditioners and subsequently recorded with data acquisition equipment. Foil gauges are usually only installed in the laboratory, as they require intricate soldering and wiring, and is usually performed by specialists. On field measurements, we usually use encapsulated gauges, as in the lower pictures. These provide protection and are pre-wired, therefore reducing the requirement for soldering on site. This reduces the installation time, and the colour-coded wires assist with the correct wiring of the Wheatstone bridge configuration. Typical applications for TFI are propeller shaft measurements of torque, bending, thrust and shear. Strain gauges are also used on fixed structure to measure the stress for establishing failure mechanisms, for example fatigue. We use telemetry for transmitting strain data from rotating or moving parts. This is where direct wiring is not possible. In the TFI case, temporary measurements are common, so battery power is usually used, but this has the obvious limitation for battery life. For longer term measurements, inductive power can be used. However, these are more difficult and time consuming to install. TFI use a number of suppliers, and it's often the case that some have advantages over other systems. Unfortunately, there is no ideal solution, and each measurement application is required to be reviewed to define the best possible solution. The pictures show equipment from various suppliers, and we have 1, 2 and 4 channel systems. For TFI measurements, there is not normally a requirement for more than 4 channels in any one location. Finally, I wish to outline some of our data acquisition equipment. The majority of our multi-channel measurements are undertaken with the CDAC system by National Instruments. It allows for quick configuration and provides a distributable system with multi-slot chassis in different locations about the vessel. All the locations can be synchronized, so all the measurements have the same timestamp, which is important when investigating most issues. Various input modules are available, however the most commonly utilised by TFI are voltage, IEPE for vibration and noise measurements, and strain input modules. The picture on the left in the laboratory shows the various chassis and modules for the different measurement types. The chassis can accommodate either 1, 8 or 14 input modules. The centre and right hand pictures are slightly more realistic, showing quite common environments encountered on site. Other measurement systems and arrangements are utilised on a job-specific basis. For example, shaft jacking measurements have a specific program, as it is a regular, repeatable process. Long-term monitoring is possible using a different chassis with its own processor and real-time operating system. These installations need to work unattended, so it is best not to use a potentially less stable Windows-based operating system. Hopefully this has provided a quick overview of the measurement types we use on site that are undertaken by TFI. Thank you for your time.
In the next part of our session, my colleague and metallurgical lab manager, Dr. Chen Zhu, and I will go through a couple of failure investigations. It was very difficult for us to choose investigations as all of our projects are subject to strict NDAs, but we have managed to provide you with highly sensitized but very interesting case studies.
Hi all, welcome to our presentation. My name is Chen. I'm the failure investigation specialist working in the materials laboratory within Technical Failure Investigation Department in Lloyds Register. Our lab is based in Chandler's Ford. It is within working distance to the Central Global Technology Center of Lloyds Register in Southampton. Working with my colleagues in the department, we are providing a sophisticated failure investigation solution to understand the root cause of marine components failures. We have the knowledge and capability to investigate a wide range of metallic components. They could be anchors, chain links, propellers, or engines, winglet shafts failures. Usually, for the materials failure investigation, it includes several different processes, starting with visual examinations, followed by mechanical tests, which include tensile tests, various types of hardness measurements, and Sharpie impact toughness tests. We also carry out fractography, which covers detailed studies of fracture surfaces to identify the fracture types, understand the fracture initiation. After that, we also carry out chemical analysis, metallography studies using either optical metallography or scanning electron microscope to establish the material's conformation to the national or international standard. And towards the end of the investigation, we usually provide a comprehensive failure investigation report to include all our findings to our clients, usually ship owners or ship manufacturers, for legal or insurance claiming purposes. Today, I'd like to use this opportunity to talk about an interesting propeller failure investigation we carried out rather recently. First, a little bit background of the propeller failure. We were originally presented with images of damaged propellers with signs of somewhat pitting corrosion features on the edge of the propeller. You can probably get some brief ideas of how big the blade of the propeller is. It is therefore not commercially viable or possible to send the whole propeller to our investigation laboratory. Therefore, we agreed with the ship owners to only machine a section which includes the interested pitting and fractured area. During the investigation, it is quite important and critical to remind the client when they're machining the section, it has to be make sure there won't be too much heat bring to the damaged area during sectioning. it looks really small comparing with the overall dimension of the propeller blade. So this is how the suction side of the damaged propeller section looks like when it is sent to our laboratory. The pitting on the suction side of the blade is usually associated with the cavitation erosion process of very well known to be associated within propeller damages. A little bit background information of cavitation erosion. Usually during the interaction between the propeller blades and seawater, the cavitation can occur when the localized pressure in the fluid drops below the vapor pressure, causing vapor bubbles to form. And after these bubbles form, they will move to the regions of higher pressure and then collapse violently, releasing a significant amount of energy. The collapse produce very localized high pressure jets that can impact nearby propeller surfaces. And eventually, the repeated impact of these microjets will cause vast damage to the propeller materials, causing pitting, surface fatiguing, and ultimately materials removal, which is very similar to what we are observing now. We usually can use computational fluid dynamic investigation to understand the process and understand the precise locations of the cavitation erosion regions in propellers, which we're not going to talk about too much in this presentation. If you're interested, there are plenty literatures available on this specific topic. Of course, we're focusing on the metallurgy investigation of the damaged propeller sections here. Similar to other failure investigations, for this one, we started with the visual examination of the section from the pressure side of the propeller. The blade has apparently suffered mild corrosion and discoloring, which is normal for the propeller blade in seawater. We usually used a type of nickel aluminum bronze, which is very likely to be this case as well. But interestingly, you can see some contrast of localized granular area, which indicated potentially there has been some welding taking place on the pressure side of the blade. The welding has various of positions and consists of both some small isolated spot welds as well as very large continuous welds. Let's look at some detailed features from this picture, which is the pressure side of the blade. The fracture path is perpendicular to the trailing edge for approximately 30 millimeters before a rather sharp 90-degree turn. Then the fracture follows a linear route parallel to the trailing edge for around 200 millimeters, apart from a central curved fracture path approximately 400 wide. Just as a reminder, some of the photos included in the presentation are directly copied from the investigation report, hence a quotation of different figure titles. For this case, they are simply magnified views of the squared area with highlights of unique contrast caused by either continuous welds or isolated spot welds. For example, figure 5 includes a crack associated with welds. The feature included in figure 6 is a shrinkage cavity which is likely to form during propeller casting process in manufacturing. And figure 8 is a secondary crack associated with cavitation. Let's review this slide again. On the suction side of the propeller section, a region of cavitation coincides with the central curved fracture where the crack was found to be continuing away from the trailing edge of the blade. The area of the cavitation is highlighted and the close-up view is inset. It is the same area as I pointed out at the previous slide. This slide is a side view of the propeller section. The two images highlight how it has been deformed. The deformation forms a roughly parabolic path, slowly increased in steepness to a central apex. There's no evidence of localized deformation that may have been attributed to impact or directly associated to the regions of the welding. As a common practice, we removed a sample from the blade and ensuring there's no weld metals included, and then sent to external laboratory for chemical analysis. The chemical analysis results are within the limit for the typical nickel aluminium bronze alloy. It is mainly copper with approximately 10% aluminium and 5% iron and 5% of nickel. It is a very common used alloy for casting, usually used in the marine environment because of its high good strength, castability, resistance to corrosion, and resistance to cavitation erosion. It is considered to be appropriate material to make marine propellers. Let's go back to the fractography of the failure. Since the fracture has a rather sophisticated path, we have to divide it into different parts and look at them separately. I'd like to mention a few terminologies we usually used in fractography analysis. First is beach marks. Beach marks are the visible lines running perpendicular to the direction of fatigue crack propagation and marking successive positions of the advanced crack point. And secondly, the ratchet marks are the lines running parallel to the overview direction of the crack propagation and is formed by intersection of fatigue cracks propagating from multiple origins. For this case, the beach marks and the ratcheting marks from the second part of the fracture demonstrated that for the bottom half of the fracture, how the fatigue fracture has initiated from the heat-affected zone in the middle of the material into the propeller casting. The discontinuity at the edge between the heat-affected zone and the casting can only be explained because of the lack of fusion during welding. Similarly, in fracture part 5 and 6, there are similar positions and morphology of ratchet marks and beach marks, all of which indicating the fatigue propagation of the crack started from the root of the heat-affected zone from the welding, and it is definitely related to the lack of fusion during welding. Besides the fractography, we also look at the metallography of the overall general microstructure of the felt components. As I mentioned before, nickel, aluminium, bronze is the materials we used here. It is a very complex alloys, consist mostly of coppers, but with aluminiums and irons and nickel. The general microstructure has various of desired phase presented there at the room temperatures. It consists predominantly of alpha phase with 4 different forms of kappa phase after precipitation during cooling when cast. The kappa phase are desirable in the microstructure as they help to increase the toughness and ductility and are only produced through appropriate cooling rate. The alpha phase is also desirable due to its ductility and is only produced through slow and cold cooling. As a comparison, we looked at the weld metal and the consequential heat affected zone next to the cast materials. Also to understand the association with of the weld to the properties of the propeller blade. The cross-section was taken through a weld along the fracture surface, highlighting the changes in microstructure after etched using etchant. The microstructural change in the heat-affected zone is very obvious. The weld metal is fused into the cast material and the heat from the process diffused into the nickel, aluminium, bronze, forming the heat-affected zone. The acicular alpha and beta phase in the weld metal and specifically during the heat-affected zone is definitely very undesirable because of its morphology. Obviously, the welding of the nickel, aluminium, bronze blade had a significant effect on the microstructure. To better understand the effects of the welding to the mechanical properties, we carried out a very localized viscous hardness survey of HV.3 through the welded section. The slide is the relative micro-hardness results of the material with respect to the depth through the welds in the second part of the fracture. The picture clearly showed that the hardest region were found in the heat-affected zone, and the hardness values changed from about 300 to around 200 over a very short distance during the transition from the heat-affected zone to the original propeller microstructure. The sharp increase in hardness can initiate fractures due to accumulated slippery stresses and the inherent brittleness of the harder microstructure. During operation of the propeller, the cyclic forces applied to the blades have clearly promoted the propagation of the fatigue fracture originated from the vulnerable microstructure within the heat-affected zone. After investigation the most damaged blade, we recommended to the client to send us the sections from the rest 4 blades from the same propeller for further investigation. And not surprisingly at all, we found very similar features as the previous blade. The fractures identified on the sections from all 4 blades are also predominantly due to the propagation of fatigue fracture originating within weld repairs to the blades. The cavitation erosion presented on the suction side of all the 4 blade surfaces are likely to have contributed to the fractures through the reduction of the blade thickness. The failure of all the blades most likely was due to the high cycle load exerted by hydrodynamic forces on the tip of the blades. The load is responsible for aggressive cavitation erosion and fatigue fractures and the deformation of the blade surfaces. There are 2 possible different scenarios of the sequence of the events. One is that the cavitation erosion started first and fatigue fractures follows, enhancing erosion rate. Another is fatigue fractures first as a sequence of the weakening of the materials by welding, triggering cavitation erosion due to the deformed blade surfaces. Based on all the previous evidence presented, we can conclude that the failures of the propeller were predominantly initiated at sites associated with weld repairs on the pressure side, and the cavitation erosion on the suction side definitely contributed to the fracture propagation by reducing the blade thickness and the sectional strength of the propeller. Also, there's no evidence of external physical damage to the propeller. Obviously, the conclusion has raised some questions of the welding practice during propeller manufacturing. Not surprisingly, it has been required in both Lloyds Register's rules for propeller manufacturing and general requirement from International Association of Classification Society that any welding should be witnessed and documented by the appropriate classification society survey, which is definitely missing in this case. Many thanks for your listening. I hope you find this a very interesting failure investigation sample. Please feel free to contact me or my colleague within Lloyds Register if you have any further questions related to any materials failure investigation of marine components. Thank you.
I have chosen the investigation of a fractured crankshaft, which includes features that are commonly observed in mechanical power transmission equipment. We were requested to determine the cause of failure of a crankshaft which had occurred between the crankpin and main bearing journal. In order to facilitate transportation and ease of handling in the laboratory, the crankshaft was sectioned and cold cut such that the areas of interest could be inspected. The sectioning instruction that we agreed with the client are indicated in the image on the left, with the fracture location also indicated. Here you're observing the components of the crankshaft after sectioning. As you can see, the surface of all sections was coated with grease by our client as we instructed to provide a form of protection. This was then removed upon receipt in the laboratory to permit further investigations. In order to fully understand the nature of the failure, it is necessary to obtain a comprehensive assessment of both the defect's morphology and metallurgical condition of the underlying microstructures about the failed and damaged region of the component. In addition, attention should be given to the local chemical and mechanical properties of the component. The results will then be compared to the materials specifications to determine the component's compliance with the specifications. In these images, you can see the location of the failure in relation to the main bearing journal and crank web. The image in the middle is the same component on the left, only taken from another angle to show the failure location and fracture surface more clearly. As I mentioned earlier, all components were cleaned to allow further investigation. Now you can see the fracture surface a lot better in these images. It is clear that failure of the crankshaft had initiated from the main bearing journal with crack propagation predominantly through the crank web. You can see the fracture surface is generally flat with evidence of a single start mark located at the main bearing journal surface. Beach marks were also observed across the fracture surface, which emanated from a single start mark. You can also see river lines in areas of the fracture surface. These features observed are indicative of a fatigue failure mechanism which occurs upon application of cyclic loading. Fatigue cracks generally initiate in areas of highest stress concentration. Sharp cracks, defects, grooves, and changing section can often act as stress concentrators, which can increase the probability of crack initiation. In the immediate areas of these stress concentrators, the effective stress is greatly increased. The initiation site was located approximately 15 to 20 millimeter from the main bearing journal to the crank web fillet radius. Now let's take a look at other features. Further investigation of the surface of the main bearing journal in the area of the failure exhibited evidence of spalling and abrasion marks. We further investigated these areas in order to characterize constituent features and defects along with the underlying metal microstructure. Metallographic examination was undertaken. A section was taken through the areas of spalling and the initiation area. The sections were mounted, ground and polished to a 1 micron finish before they were etched in a nitrile solution in order to reveal the underlying microstructure. The final sections revealed evidence of a hardened layer at the external surface of the main bearing journal. It was evident that the fracture initiation area was adjacent to the extremity of this induction hardened layer. I have to note that the depth of the hardened layer was then found to be consistent with that specified for this component. Further examination of the external surface of the main bearing journal revealed evidence of cracking associated with the spalled areas, some of which had propagated parallel to the surface. In several areas, the spalling and cracking observed was associated with a white etching layer considered likely to be untempered martensite. White etching layer can be intentionally produced to create a surface hardened layer. However, the intermittent nature of the layer and its confinement to the areas of spalling indicated that the layer is attributable to wear. The white etching layer signifies a phase transformation from the quenched and tempered martensite into austenite and subsequent transformation into martensite during rapid cooling. To reach the austenitizing temperature, the material needs to be heated up to a flash temperature of 723 degrees centigrade. The nature of the spalling observed may suggest that the damage is attributable to surface or sliding contact fatigue. And sliding contact fatigue commonly found in components that slide against each other under high contact pressure and which are susceptible to development of surface pits or spalls. It is thought that the spalling damage acted as a stress concentrator for fatigue crack initiation. For chemical analysis, a section was removed from the main bearing journal and analyzed by optical spectroscopy. The analysis was generally consistent with the grade, with the carbon level being marginally higher than the specified range. Vickers hardness testing and micro Vickers hardness testing was also conducted at the core and through the hardened layer of the main bearing journal, using a 10 kilogram load for Vickers hardness testing and 1 kilogram load for micro Vickers hardness testing. The results and the depth of the hardened layer were then found to be consistent with that specified for this component. So far, it was determined that the failure had occurred due to a fatigue fracture mechanism. The nature of the spalling and crack propagation suggests that the damage is attributable to sliding contact fatigue. The area of a spalling and wear would have acted as a stress concentrator for fatigue crack initiation. Materials investigation also confirmed that the specified hardness has been met. Chemical and mechanical properties of the main bearing journals was found to be consistent with that specified for this material. It is thought that the breakdown of the hydrodynamic oil film between the bearing and journals caused the wear and spalling observed. These areas then acted as a stress concentrator for fatigue crack initiation. It is likely that the presence of oil-borne debris particles and/or debris embedded in the bearing surface resulted in the formation of hotspots leading to wear and spalling. The spalled particles can then significantly exacerbate further wear and abrasion, leading to formation of fatigue cracks. Typically, the hydrodynamic oil film in bearings can vary between 2 microns and 20 microns thickness, dependent on pressure, viscosity, and crankshaft dynamics. Thus, for thin oil films, it does not require a significant amount of or large debris particles to generate disruption in the oil film. On behalf of Lloyds Register and British Gear Association, I would like to thank you all for your time joining us today for our Technical Awareness Day, and I hope you found this session useful. Please don't hesitate to contact us if you have any further questions.